Let us look at factor theorem. It says a polynomial fn of x is divisible by x minus alpha if and only if alpha is a root of the equation fn of x equal to 0. So alpha can't be anything, any number. It has to be the root. Now, a brief background. We say 2 divides 6, written as 2 bar 6. That is 6 is equal to 2 times 6 plus 0. That is a 0 remainder. So when we have a 0 remainder, we say 2 divides 6, which is written as 2 bar 6. But we cannot say 2 bar 9. Since 9 is equal to 2 times 4 plus 1, that is a non-zero remainder. So keeping this in mind, let's see what happens in the factor theorem. It says if x minus alpha divides fn of x, that is x minus alpha divides the polynomial, implies remainder is 0. Therefore, fn of x is equal to x minus alpha times q plus 0, which is equal to x minus alpha times q, where q is a polynomial of degree n minus 1, which implies fn of x is equal to 0 when x is equal to alpha. Does that mean fn of alpha is equal to 0? So therefore, alpha is a root of the equation fn of x equal to 0. Now let's look at the converse of this. So conversely, alpha is a root of fn of x equal to 0. We start with that statement, which implies fn of x is equal to x minus alpha times q plus r, the remainder part. Substituting x with alpha, because alpha is a root of fn of x equal to 0. We get fn of alpha is equal to alpha minus alpha times q plus r. Alpha minus alpha is 0 and fn of alpha is equal to 0 because it is a root. So we have r is equal to 0. This is 0. Alpha minus alpha is 0, which means alpha minus alpha times q is 0, which means r is equal to 0. And therefore, because there is no remainder, that means this root alpha divides fn of x. Therefore, x minus alpha is a factor of fn of x. Now, previously, to find the roots, we guessed small integer value of x until we found a root. Using this root, we divided the quadratic or the cubic expression by x minus r1 using long division to get the second factor, which is what this theorem is all about. So that was factor theorem. That's it for now. Bye.